Okay. For any family of the organic molecules, when we study the family, for now we're studying the family of alkane, we want to know the hybridization, the structure formula for the functional group, which we don't have the functional group, so the hybridization for the carbon for alkane is sp3, the bond angle, and naming these compounds, how to name the organic molecule for every family. It's the major part of the chapter for every family that we study. After naming, we want to know about physical property, which we briefly talked about physical property yesterday. Physical property is due to intermolecular forces. Intermolecular forces for alkane is van der Waals forces. So for the van der Waals forces, we are looking at the weak type of intermolecular force, the boiling point, melting point for alkane molecules. It's low, but it is higher for a straight chain, straight carbon chain alkane compared to branched. And as the number of carbon per molecule increases, basically as the mass increases, van der Waals forces is going to increase, be stronger. So intermolecular forces is stronger, and the boiling point is going to be higher. There are some patterns that you have on this slide. Boiling point, if you have the normal alkane, which means the alkane without any branches. You have the blue line here, the pattern, and for the isoalkane, which is just one branch of methyl group on carbon number 2, the pattern shows with the green line that in general boiling point is lower than the melting point. I'm sorry, boiling point is lower than the comparable or same number carbon alkane with no branch. So the branch is compared with the no branch. Melting point is compared for the for alkane, and here, like interestingly, as the numbers, if it's odd or even, they are slightly different. And in general, the greater number of carbon per molecule, the greater the melting point is going to be. Like if you have a molecule of with 4 carbon, just alkane is going to be gas at room temperature. But if you have a 14 carbon alkane is going to be solid. Between 5 and 8. So you have octane. If you when you go to like when you go to gas station and you try to pump gasoline and gas in your car, you're basically is the liquid form of the alkane. So the rating of like isooctane rating. So if you have like 89 or if you have 90, 91 or 93, that actually shows the rating of the isooctane. And when you have the greater number or percentage of that is going to be, I guess, combustibility is better, or you get better gas per mileage with the gas that you're using. So the reason I mentioned that is just that if you have like 8 carbon, it's going to be liquid at room temperature. But if you have like 14, 15 carbon or greater, it's going to be solid at room temperature. So the greater the number of carbon per molecule, the higher the melting point. And if the melting point is higher than room temperature, it's going to be solid at room temperature. If the melting point is less than room temperature, it could be liquid or gas at room temperature. So it depends on how low is the melting point. And some of the application or sources and uses of the alkanes are shown in this slide, and you can look for more. Some of the reactions of alkanes is the combustion. Unfortunately, that's the worst type use of alkane, but that's the most popular use of the alkane, like burning of the alkane for creating more energy. Because if one molecule of alkane combusts, that combustion means the combination of every element of the alkane or the compound with oxygen. So in combustion of alkane, you would get carbon combining with oxygen, you get carbon dioxide, and then hydrogen combining with the oxygen, you will get water. So the product is going to be carbon dioxide and water. To balance this equation, you should always balance the number of the carbons from right to left, number of the hydrogens from right to left. So for every carbon, you get one carbon dioxide. For every two hydrogens, you would get one molecule of water. And when you are trying to balance the oxygen, you would go from left to right. You count how many oxygens you have, and then you can balance the equation. So in general, combustion reaction of alkane, you would get carbon dioxide and water as the product of the reaction. The other type of reaction for alkane, we have cracking and hydrocracking. What does cracking means? It means you cut the molecule in half. So when you do cracking of the CN, let's say you have C4H10, and you try to do cracking of this reaction. So cracking, you are going to use energy. So a bit higher number. You have C8, for example, and then how many hydrogens should we have here? 18. If you crack this, basically you give energy, you cut the molecule in half. So when you are cracking, you are breaking a carbon-carbon bond. Let's say if you crack it evenly, you would get 4 carbon in one molecule and 4 carbon in another molecule. How many hydrogen should you get to the first carbon? First 4 carbon. Just to satisfy is going to be 10. And then to the other molecule, there's only 8 left. So if you have a C4H10, you're going to have a saturated hydrocarbon here, 1, 2, 3, 4 carbon with 10 hydrogen. And if you have 4 carbon with 8 hydrogen only, this must have one double bond. So if you do cracking reaction, you don't provide any hydrogen to when you are breaking the carbon-carbon bond for alkane. You basically are going to get one alkane molecule, and the other one is going to be alkene because it's lacking 2 hydrogen. When you break the one carbon-carbon bond, you must provide extra hydrogen if you want to satisfy or saturate the other molecule. So that would be cracking, the first one. If you do hydrocracking with that molecule, with the 18 hydrogen, you also add 2 extra hydrogen. Now you could get 2 molecules, both of them with C4H10 and C4H10. So you have to provide extra hydrogen. Why can't each get 9 hydrogen? If each one gets 9 hydrogen, then the structure, the loose structure is not going to make sense. Then you are going to get carbon with empty orbital. So the number of bonds is not going to be satisfied with 9 hydrogen. So with the 9 hydrogen, you are going to have 1 carbon that is going to have 3 bonds. And with the 3 bond, it doesn't, the loose structure is not going to be correct, and the octet is not going to be satisfied. So hydrocracking is breaking carbon-carbon bond, and you are also providing hydrogen. And cracking is when you are breaking carbon-carbon bond in half, and then you're not providing hydrogen. So one of the product is going to be alkene. The structures and the conformation of the alkane. Alkanes, the structure of formula, if I use the model here for the atom of the carbon has 4 bonds, and that those 4 bonds to 4 hydrogen. So this would be the 3D structure for the for molecule of methane. 1 carbon and 4 hydrogens. Let's see if I can get these so you could see easier. So you have the molecules of this would be the 3D structure for the methane. You have 109 bond angle. Hybridization is sp3, and it's any directions is like all symmetrical. Any direction you are going to rotate is going to look the same. So it's always 1 carbon. If you look at it this way, if you hold it, you should normally hold the molecule in a way that 2 hydrogens and 1 carbon are in one plane. So you have a carbon, a hydrogen, carbon, other hydrogen in one plane. Then you see 1 bond is going away from you, and then 1 bond is coming towards you. So when you draw the structure formula for methane, you also drawing like this. You see the solid lines that you have there. You have there the solid line is showing the hydrogens that are in the same plane with the carbon. So we have 2 dash line here, and then we have this the 2 triangles. That one triangle is like filled, and then the other one is like dashes. So you have the wedges and dashes. So with these, the one that is showing with the dashes, that means it's going away from you, and the one showing with the wedges is coming toward you. So the solid triangle, that's the bond that is showing is coming toward you, and the other one with the dashes is going away from you. So you always hold the molecule in a way that 2 bonds are aligned or with the same plane as carbon, and then 1 bond is going away and 1 bond is coming toward you. This also is important when you're studying the stereo chemistry. That's for methane. Now, if it's ethane, you have a CH3. So you basically take one of the hydrogens away, and you're going to add another carbon with the 3 hydrogens. Okay. Now we have the structure for CH3. This is the structure for ethane. So 2 carbon, 6 hydrogen. How is the orientation in the space? We said that the rotation around carbon-carbon is not free of energy. It takes like 3 kilocalorie per mole, and the room temperature can provide that. So basically, you can rotate this carbon-carbon bond. When you rotate the carbon-carbon bond, see how it's different. So when you look at it this way, you may not see much of a difference here. But if you look this way, basically you take the the carbon-carbon bond and you place that in your view. So your view is going to be in carbon-carbon bond aligned together. And when it's aligned together, basically one carbon is hidden behind another carbon in your view. And when you look at this, like if I hold it perfect aligned, the carbon-carbon, you see at this position, the hydrogens are also covering each other. And since the rotation around carbon-carbon is free, so rotation is possible, I can start rotating this carbon-carbon bond. And as I rotate carbon-carbon bond, what do you notice there is that sometimes the hydrogens are covering each other. So the two hydrogens, one from each carbon, is kind of covering each other. And other times they have more space between them and they are not covered. So if you take a ruler, I don't have a ruler here, but if you take a ruler and measure the distance between these two hydrogens under this condition and rotate it, when you could see the hydrogens from the other carbon and you measure the distance, this is great. It gives you greater space between the two hydrogens. So if they are covered, this is known. This structure is not a structure former, it's basically conformer. This conformer is called eclipse when the two extreme case, when the hydrogens are covering each other completely, is known as eclipse. And then you start rotating. As you rotate, the distance between the hydrogen is increasing, the repulsion is decreased, the steric hindrance is less, and this area is going to be the maximum. So this position is called staggered. So we have a staggered when the hydrogens are as far as possible from each other, and then the eclipse when you get the hydrogens covering each other and they are as close as possible to each other. So this rotation around carbon-carbon bond, it can go from eclipse to staggered, and again from staggered to eclipse, and it can rotate. So when you see like an energy diagram, which one is going to have lowest energy, eclipse or staggered? Staggered is going to have lower energy. So stability is the lower energy. The lower the energy for or internal energy for the molecule, the more stable the molecule is. And what makes one conformer more stable compared to another molecule is the steric hindrance in this case. And the steric hindrance is lowest when you have a staggered position. When it's eclipse, that would be the highest energy. So when you have higher energy, it's going to be less stable. When you have lowest energy, it's going to be more stable. What causes this more stability is the space between the hydrogens. So hydrogens are a small group. So they are not very problematic. But if you change the hydrogen with the bulky group, this staggered and eclipse is going to be more significant, and they are going to be different. They have different energy, and the energy difference is going to be more significant. So that's for ethane conformer. So when we are rotating this, we are not changing the orbital overlap. We are not changing hybridization. We are only rotating around carbon-carbon single bond, and we hold the molecule in a way that the carbon-carbon line, it passes like from our view. So in a way that one carbon is hidden behind another carbon. So you would see this in one line only. So then you start rotating. So we have two conformers for ethane. We have one conformer for methane, or one structure for methane. but for ethane we have two conformers. If we move to the next molecule, let me see, I have an energy line for this to show you. So the orbital is not going to change, the orbital covering of orbital overlap. You still have the sigma bond for all of them. So you have single bond. You're just rotating. When you do rotation, it goes from staggered to eclipse and eclipse to staggered. The representation for staggered and eclipse sometimes is not easy when you do like a 3D structure, like the all in one line, but Newman projection is a projection of eclipse and staggered that is trying to make it easier. So basically you draw one line, one circle is not the perfect one, and one is showing, that would be the circle that is showing the hydrogens that they are in your view, and then the other carbon is hidden behind. So you only draw one circle showing the first carbon. The hydrogens that you could see, if they are in your view, you are going to draw them with the full bond length. So you have your 3 hydrogens that you could see. With the hydrogens that are away from your view, you would draw them with the smaller line. Kind of for the eclipse is going to be hidden behind each hydrogen. So you would just, the bond length, or what is showing here, you're just is representing the presence of the hydrogen behind the hydrogen that is in your view. So the full circle is going to show the first carbon, and full bond length is going to show the hydrogen that they are bonding to the first carbon. The one behind, the carbon behind, is hidden, so you're not going to see the carbon. You only could see those hydrogens as you rotate slightly. So we know that there's hydrogen behind this hydrogen, the blue hydrogen, there is this like a red hydrogen that is attached. So if you see this small line showing the bond for the hydrogen, that means that hydrogen is attached to the carbon in the back. So if this is the eclipse structure for ethane, for Newman projection for staggered, you're going to draw the line, draw one circle, full circle with the full bond length, the hydrogens that is shown. They are at your the carbon in your view. Now, if I hold this in a staggered position and try to draw the hydrogens, they are going to be in between, visible, but you still have to show with the like short bond length, and it starts at the edge of the circle. It doesn't start from center because you don't see that. It's going to be hidden behind. So for the carbon that is behind, is out of your view, you would start the bond from the edge of the circle, but for the hydrogens that are in the attached to the carbon on your view, you would start from the center. Any question about Newman projection for ethane for now? Okay, so it's just the drawing that you need to be able to draw the Newman projection, and then look at the energy diagram. So for the eclipse, we have the highest energy, and how do we know it's eclipse? Because these hydrogens are covering each other, and the staggered is going to have the lowest amount of energy for ethane. This is for ethane. How do we know we have ethane? Because it shows only 2 carbon, and when you draw the circle, that's just showing 2 carbon. Even if you have more than 2 carbon, you only take 2 carbon for your view. So anything else is going to be branched off of those 2 carbons. and we have the eclipse staggered, and this is just moving around. And if we look at this area, which is not that energy diagram, and that energy diagram, if we look at point A here, that's somewhere in between, is not the full eclipse and is not full staggered, because when it's eclipse, we have the highest energy. When we rotate, the energy is going to be lowered, okay, gradually until we get to the minimum amount of energy that represents the maximum distance between the hydrogens. The hydrogens from attached to carbon 1 and the hydrogens attached to carbon number 2. So the difference in energy here between the eclipse and staggered is about 3 kilocalorie, or 2.9 or 3 kilocalorie. And this energy, it would be provided at room temperature. It's not a lot of energy. Now, if we move to the next molecule, what's our next molecule? After ethane, we go to propane. Yes. After ethane, if we move to propane, right? Okay, this is the molecule for propane. Now, CH3, 3 hydrogen attached to the first carbon, CH2, 2 hydrogen attached to the second carbon, and then we have CH3, 3 carbon attached to the other carbon, last carbon. So we have CH3, CH2, CH3. Now, if we hold this molecule for the most stable position, for the Newman projection, or trying to figure out the staggered and eclipse position, the rule was we only take 2 carbon for our view. So we're not going to be like, okay, where should I look? Should I look from this end, or like this? What angle should I look at this molecule in order to determine the strain or the steric hindrance, how it's going to look like? So the rule is, or to draw the Newman projection or determine the conformers. For alkane, we are going to take 2 carbon again. So I'm going to take the carbon 1 and 2 and hold it in a way that carbon 2 is covered by carbon 1 in your view. So if carbon 2 is covered with, in your view, if you look at this molecule now, the hydrogens are covering on this side, and this top hydrogen is covering a bulkier group, and your bulkier group is a CH3. So same idea, we are going to start rotating. Now this is going to be eclipse, right? Because they are covering, the groups are covering. I'm going to start rotating this. So when I rotate, the distance between the hydrogen and other hydrogens, and in this case hydrogen with methyl group, is going to increase. Slowly is increasing, and now is the maximum distance. So we have the maximum distance. So we can call, again, similarly, we can call this as a staggered, because the groups are not covering. You could see the hydrogens from the other carbon. And if you rotate slowly, the energy now is going to increase. The distance is decreasing. In this point is a full coverage. It goes to eclipse. So by rotation, again, we are going from eclipse to staggered, from eclipse to staggered. To draw the energy diagram, we can see just one minimum. That's the staggered position, showing the staggered, and then one maximum energy, which shows the minimum amount of the stability or maximum energy, that would be Eclipse. Eclipse, the distance between the hydrogen is the lowest. The internal energy for the molecule is the highest. Stability is going to be lowest. So we have two conformer, two extreme conformer for the propane as well. So that would be Eclipse and staggered. The difference in energy, if you are comparing with Eclipse, is going to be greater than staggered. But if you compare propane to ethane that we had before, what's the difference? For ethane, you had all hydrogens. You were dealing only with hydrogens. Here, you are dealing with hydrogen with the bulky group. The strain between the hydrogen and the bulkier group is going to be greater. So the difference in energy of Eclipse and staggered for propane is going to be 3.3 compared to 3 for ethane. So for ethane is 3, for propane is going to be 3.3. So it's just a 0.3 kilocalorie difference in the energy. So, but is more stable when it's staggered, less stable when it's Eclipse. So we have two conformation, also two conformers for propane as well. To draw the Newman structure for propane. Again, the Newman structure is presented here, but I'm going to draw with you, so you could just, when you're drawing your own Newman projection, when you have the 3D structure, or when you have Eclipse, or you have the staggered position. For propane, the first circle that shows the carbon at your view. So we use the full length, and we start from center to draw the hydrogen. We have 3 hydrogens. What's on the other carbon that is out of your view? We have 2 hydrogens and we have 1 CH3. For the Eclipse positions that I have right now, in the model that I'm showing you, there are hydrogens that it's hidden behind this hydrogen. So we start the bond from the edge of the circle, and we have 1 hydrogen here, and the third one is a CH3. Now, which one should I write CH3? Which two should I write hydrogen? It doesn't matter, because this rotation is constant rotation, and it's constant rotation that even these molecules, like from Eclipse to staggered, you cannot separate them off. For propane, at least, you cannot separate it because the energy difference is so low, and the molecule keeps rotating to get to from staggered to Eclipse. You can't freeze it in one position of Eclipse or freeze it in one position of staggered and separate and bottle it separately. But when the energy of the molecule is studied by rotating the molecule, it shows that energy of the molecule, it's when they're trying to study the internal energy for this molecule, see that it's changing. It's not constant. It's not just one number. It's not like methane. So this molecule, it shows like energy diagram. So you will see that energy is going down and then it goes up. And then they study this, the possible conformers, and then they come up with like 2 extreme case, that one is staggered with the lowest energy and one is Eclipse with the highest energy. And that's for the, I'm sorry, it should be CH3 here. So we have 2 hydrogens and 1 CH3. So this strain between hydrogen and CH3 is greater than hydrogen-hydrogen, but that makes the whole molecule for propane Eclipse and staggered by difference of 3.3 kilocalorie, which we have here. Okay. Any questions about conformers for propane? Eclipse and staggered. No, you just need to know, you don't have to know the exact numbers. You just need to know that the strain is stronger for propane compared to ethane, because one of the group is bulkier. You just have to be able to justify it. You don't have to know the exact numbers. Okay, this is not good. I have to get the second box of the model so I can. Okay, next molecule is going to be butane. Butane with 4 carbon. Okay. What do you think of this molecule, this conformer of the butane? Stable or not stable? Not stable. We have 2 methyl groups that they are very close to one another. And if I rotate this, what about now? The 2 methyl groups are as far as possible from each other, so this is the most stable. And when we draw the line angle structure, you notice that the line angle is drawn like a zigzag, like this, going up and down. It's not just that they like the zigzag better, but when you look at the structure formula for a alkane, the maximum distance of the groups from one another is provided when you have your carbon chain in a zigzag form. See, it's going up and down, up and down. This provides the maximum distance between the groups that are on the opposite end. If you rotate this, you can go to the minimum distance and the highest internal energy, the most unstable conformer for butane. So for butane, we are going to take the carbon. So if I number these carbon, this carbon is going to be carbon 1, 2, 3, and 4. Does it matter which way to number it? No, but I'm going to just take this one as carbon 1, carbon 2, 3, and 4. To study the conformer of butane, we are going to look through carbon 2 and carbon 3. So this is how we are going to look. So we look at carbon 2 and carbon 3. And we rotate around carbon 2 and carbon 3. So for carbon 2, we have 2 hydrogens attached and 1 methyl group. For carbon 3, we have a methyl group attached and 2 hydrogen being attached. So when you study the conformers for butane, you are looking at carbon 2. Carbon 3 is going to be behind carbon 2, and you are looking at the carbon 2, carbon 3 line. And you study how close these groups are to one another. So what would you call this for butane? Eclipse or staggered? Eclipse. And it is a totally eclipse. Totally eclipse, it means that you have 2 bulky groups of methyl facing each other. This would have the highest energy of all conformers of butane. So we are going to look at the carbon 2 and 3. The Newman projection, I'm going to bring the Newman projection. I will draw the Newman projection for you, but I want to look at the energy diagram for you. So we have maximum amount of energy when it's totally eclipsed. So if you look at the energy diagram, you have A, that it gives you the maximum energy, and then you have D here that gives you the minimum amount of energy. So if we have the maximum amount of energy that is coming from the conformer, that you have two metal groups facing each other, this is the least stability for the molecule. And then D would be when you have the two metal group as far as from each other, and this gives you point D of the energy diagram. With the point D of the energy diagram, you have your anti. That means that it's in the opposite directions, opposite end. The two are in the opposite end. I was looking for the names for the different conformers for you. Okay. So what about this position here? If you're looking this, true carbon 2, carbon 3 is in the back. What about this position here? Eclipse or staggered? That's also, actually this one is going to be eclipse because you have hydrogen and covering the hydrogen covering metal group, and this metal group is covering the hydrogen. This is also eclipse. What about this one? For this one, you could see the metal group from behind. You could see the hydrogens. So this is, again, staggered. And this is eclipse. That's staggered, eclipse, and staggered. But we had two types of eclipse and two types of staggered. So now we have to give like different name to this eclipse and staggered because we cannot name all the same. Why we cannot name this eclipse same as this eclipse? Because both of them are eclipse. See, in eclipse 1 you have two metal groups very close to one another. In eclipse 2 you have hydrogen covering the metal group. You have the metal covering the hydrogen group. So you have two types of eclipse for butane. And when you're looking at the staggered, you have one staggered that the two metal group are as far as possible from each other. They are opposite end. And then you have one staggered that they are not covering fully. They are not covering fully because you could see the hydrogens from this angle in between, but they are still relatively close to one another. They are not as far as the two metal group are not as far as possible from each other. So point D of the energy diagram would be this, when you have the metal group as far as possible from each other, and the point A, it would be this one, when the two metal groups are as close as possible to each other, or the worst case scenario for this butane, because it's going to have high internal energy. So butane is going to have more than two conformer. So we have one conformer that it's the bond angle or the angle strain is the maximum. So you have your the viewing along the C2 and C3 bond. We have the staggered and we have the eclipse conformation, and when you rotate it, you're going to get, when you're rotating like by 60 degree, you see 0 angle, and then the 60 degree you get staggered, another 60 degree you get eclipse, then you get staggered. And let's count how many conformers you have for butane. This would be 1, that is the totally eclipse. Why do we call it totally eclipse? That would be the highest energy that's two metal group are facing each other. And you have this staggered. So this staggered is going to be not covering each other, but the two metal group are not as far as possible from each other. Then you have eclipse, that is hydrogen is covered by metal group, so that's conformer number 3. Then you have anti or anti position. The two metal group are as far as possible from each other. So you have 4 different positions. So let me highlight this. So you have the eclipse for A, the metal groups are as close as possible to each other. Then you have the anti, okay, the opposite, they are opposite from each other. That would be the point D. So you have your point A of the energy diagram, or this diagram. You have the two metal group are as close as possible to each other. So that is the totally eclipse with the least stable. And then you have the two metal groups that are opposite from each other, in opposite sides from each other, as far as possible from each other, and that would be the anti or opposite side. So this anti name is coming from the opposite side. Then you have when the point B, which is same as point F here. These two are the same. When you have the two metal groups close to one another, but they are not covering. And then you have your point F and C, which are the same. F and C are the same here. So 1, 2, that would be D, and 3, B, F, the same, and then C and E are the same. So B and F are the same. They are eclipsed, but they are not anti. I'm sorry. B and F, they are staggered, but they are not anti. Staggered meaning that they are not covering each other, like A. The groups are not covering each other, but the metal groups are not as far as possible from each other to reach the stability of the D. So this is known as a Gooch confirmation. So B and F is going to be Gooch confirmation. Now, the pronunciation of the Gooch or Gooch, it's kind of different by different people, different accent, but that's how you write it, and this is how you read it. A Gooch confirmation. So, a Gooch confirmation, that is going to be staggered. So we looked at the total eclipse. So we have eclipse, we have anti, and we have the Gooch confirmation. Okay, a Gooch confirmation when you have the staggered, but there is not anti. Anti is D. Yes, D is anti. Anti or anti. So anti in opposite position. So that would be D. And then as close as possible, the two metal group as close as possible, that would be A, point A. B and F, they are the same. These two are the same. Where they are not covering each other, but the metal group are not as far as possible from each other. And then the only thing that is left is C and E. So this dihedral angle is the angle, when you look at the dihedral angle of 0, that is the angle between the methyl group, say the group from methyl group attached to the carbon 2 and a methyl group attached to carbon 3. So if you look at these in the totally eclipse form, you have a 0 dihedral angle. So when we are talking about dihedral angle, it's not on the same carbon. It's the bond or the line that is aligned with the methyl carbon 2 and methyl carbon 3. So when we have 0 angle there, that is a totally eclipse. What would be the angle now? What's this angle between these two lines? The bond angle now is a 180. So if you take these two lines together, it's like you basically are holding the two lines like this. That's the methyl group attached to carbon number 2, and this is a methyl group attached to carbon number 3. So when it's 0, that is totally eclipse. And for the anti, you are basically taking it like this to 180 degree. So 0 dihedral angle, that would be totally eclipse, and 180 is going to be the anti or anti position. Okay. So you have A, totally eclipse, D is anti, B is minima, and F, these two are the same, and that is the Gooch. So what about C and E? C and E, that's this position again. It's covering, but hydrogen is covering methyl group. And here methyl group is covering hydrogen. It's not two methyl group covering each other, which is the worst case. When this is better covering, more stable than if you had the two methyl covering each other. So this is called eclipse. This is called totally eclipse. So we have totally eclipse and we have eclipse. If it's eclipse, it's the hydrogen covered by methyl group, just like propane. But when it's totally eclipse, you have the two methyl group covering each other. The amount of the energy is much higher, is a 4.5. Now, what type of questions you would expect from this, or what do you need to know? If you are given these all together, or maybe one of them or two of them, and you are giving this graph, you should be able to match which point or which conformer goes to which point of this energy diagram. So this one is going to be which diagram? Which point of the diagram? This one. What point of the diagram would be this structure here? That's a total eclipse, and what point of diagram? We are going from A to F. So that would be A. This one? Structure 2. This would be F, because it's not covering is not eclipse, but it's not as stable as D because the methyl groups are close to one another. Methyl group, the bond angle between the dihedral angle, not the bond angle, dihedral angle between the methyl group here is a 60 degree. 2 would be F. And this one, 3. Three would be C or this one, both of them. This is going to be C, because is eclipse, but is not totally eclipse. Okay, this is going to be eclipse, but is not totally eclipsed. Totally eclipsed is when you have the two methyl group covering each other. This is eclipse, but hydrogen is covering. Because hydrogen is not bulky, the stability for 3 is greater than 1. Stability for 3 is greater than 1. So we have 1 energy level, 2 energy level, 3 energy level, and 4 energy level for 4 different conformers. The totally eclipse and the anti or anti is the same. I'm sorry, it's easier for you because it's just like ethane and propane, totally eclipse, and then you have staggered or totally staggered, but we call that anti because the bond angle is a 180, opposite direction, exactly in opposite direction. And these are overlapping or zero bond angle. So dihedral bond angle. When it's 0, you have the highest energy. When it's 180, you have the lowest amount of energy. And then for B is 60, and the dihedral angle you have when you have 120 for the between the two methyl group. Okay. Any questions about Newman projection? How to draw the Newman projection? And these are, here you have the names again for all 4 of them. So you have totally eclipse, you have Gooch or staggered, you have eclipse, and you have anti. So Gooch is staggered, anti is totally staggered. Okay, Gooch is staggered and anti is totally staggered. Then you have eclipse and total eclipse. So if you learn it kind of eclipse covering each other, and then totally eclipse when you have 2 methyl group covering each other, that's kind of a specific case. Those 2 are easy. So you have eclipse, but this is totally eclipse. So you have 2 out of the way. Then anti is kind of easy for you. So you have 2 case that is eclipse, 2 is that is staggered. So eclipse, this eclipse is totally eclipse. So that's the first one. The eclipse that you have hydrogen and methyl group is just called eclipse, not totally eclipse. And the other 2 case would be staggered. So when you have a staggered, when you have a staggered that is not anti, is going to be Gooch. So Gooch is a staggered, but anti is totally staggered or opposite direction. So we have the totally eclipse when you have 0 angle, dihedral angle between the CH3 molecules. Cycloalkane. What is cycloalkane? The smallest cycloalkane you could have is a 3-member ring. But if you try to get cyclobutane, so if I try to get cyclobutane, I'm going to do this one more time. You see, if I'm going to form cyclobutane, this is butane. I have to make sure that the carbon 1 is attached to carbon number 4. The white balls, they are representing hydrogen in this molecule. So if I want to take my butane and change it to cyclobutane, see, I'm taking 1 hydrogen away, from one carbon, and I have to take another hydrogen away from another carbon, and then connect these two carbons. So cycloalkane, it doesn't have the CnH2n plus 2. It's just the CnH2n, because the bond, one bond between carbon-carbon from head to tail, from the first carbon to the last carbon, is going to take care of two hydrogens. So in order for me to have this bond angle, I was forced to take two hydrogen away, because one carbon cannot have more than 4 bonds. So the general formula for cycloalkane, as a result, is going to be CnH2n. So if we have a C3H6, for this molecule, there are two possible structures. One is the cycloalkane, and the other one is going to be CC double bond C. Okay, but how do we differentiate between these two? In the lab, you could add bromine. This is like a double bond, or when they measure the bond length, this is going to be shorter than this carbon-carbon single bond. Or hybridization is going to be different. The bond angle is different. But in this case, this is the general formula, CnH2n for cycloalkane. Alkene, you learn later in chapters like 6 and 7. So we have the cycloalkane. If we have three-member ring, for three-member ring, I have to get 3 carbon and 6 hydrogen and form a cyclic form. It's not easy. Why is not easy? I mean, it's really hard. Literally, I'm not faking. I'm trying to make this to form bond, but it's not easy. And why is not easy? See how much of pressure this small cyclic system is under. What is hybridization for this carbon? How do we find hybridization? Practice that prior chapters. Hybridization, you count the bonds attached to this carbon. There are 4, so it's going to be sp3. If the hybridization is sp3, what would be the bond angle? Bond angle, it's going to be 109. So for sp3 hybrid, the bond angle is expected to be 109.5. Oh, you see that it just popped out? I was holding because it's going through too much force, too much pressure, too much strain, and that is called angle strain. And why it's called angle strain? Because this 109 that was supposed to be, or ideally here is supposed to be 109, we have forced that to come down to, because it's a triangle, and each angle here is going to be 60 degrees. And you are forcing this angle to close by 49 degrees. That is a huge strain that you are putting in this angle. So first opportunity for this molecule is going to pop out open, because if it's open, now definitely this angle is 109, this is 109, and all of them are 109. So the angle strain is one factor that makes the open chain alkane more stable than cycloalkane. So what about when I'm forming cyclobutane? What is each angle here when you have a square? Is a square, right? So the total angle for this is going to be 360, and we have 4. Each one is going to be 90 degree, 90 degree, 90 degree. Is expected, or in theory, this is supposed to be 109. Why is supposed to be 109? Because hybridization is sp3. So for sp3 hybridization, we are expected to have a 109, but is strained. is pressured to go and form 90 degree. So cyclobutane is not very stable either. If I change this to cyclopentane, cyclopentane is slightly more stable. The cyclopentane is slightly more stable. And how do we justify that? Because what is the bond angle for cyclopentane, each bond angle? Do you have any calculation? Do you know what is the bond angle for cyclopentane? 108? No, 108 actually. For pentagon is going to be 108. And how do you calculate that actually? Because I don't want you to memorize it. What happened? There is a formula that you can actually calculate that. What should be the angle? The total angle for a perfectly symmetrical, like you have a triangle, then you have a square, you have a pentagon. You would say n minus 2. I think it's n minus 2 times 180. That would be total bond angles for the inside of a triangle or a square or pentagon in this case. So if we have 5 side, is going to be 5 minus 2 times 180. That's 3 times 180. What's 3 times 180? 540, right? 540, that's the total. How many angles do we have for this cyclopentane? 5, and then you divide this by 5, and you get 108. That's how you get your 108. So is cyclopentane more stable than cyclobutane? Yes. And why is more stable? Because this pressure that is on cyclopentane is only by 1 degree. And sometimes this stays like an open envelope. So 4 of them are in one plane, and then it's one is coming higher level. And it stays like an open envelope. And this is not restricted to this position. It can go down, and then one could go up. It could go down, and one could go up. So cyclopentane is more stable than cyclobutane. Cyclobutane is more stable than cyclopropane because of the angle strain. So when you have a cyclic system, the only 2 cyclic systems that they are considered to be more stable is a cyclopentane or cyclohexane. Those are the 2 stable cyclic systems based on the angle strain. So that's for cyclopentane. I'm going to give you the structure for the other cyclic system also, cyclohexane. For cyclohexane, I have lost some bonds here. I'm gonna have to. I don't have enough bonds, so I'm trying to figure out to put the proper positions. I have equatorial down, up, equatorial down here. And then okay. Okay, cyclohexane. Cyclohexane, it can be also different conformers of cyclohexane. And we probably finish this today. Hopefully, gonna get everything. So I have equatorial up, down, equatorial up, equatorial down here. And axial up. Okay. Cyclohexane. 6 carbon. How many hydrogens? 6 carbon with 12 hydrogens. And that's cyclohexane. Structure for cyclohexane is unique. We have chair conformation for cyclohexane. Chair conformation, when you place in the chair conformation, is the most stable structure for cyclohexane. And how do you build the chair? You see this like 4 carbon here in the same level. That kind of forms the seat for the chair. 1 carbon is coming up slightly. That's for the headrest. And then 1 carbon is below the level of these 4 carbon that are on the same level. And that's like a footrest. So you have your 4 carbon flat for the seat, 1 carbon higher for the headrest, and then 1 carbon lower for the footrest. So when you build the molecule, that's how you build it. When you draw the molecule for cyclohexane, you would draw it like this. So you have your headrest here, footrest here, and then you have the 4 carbon that are for the seat. So when you draw the structure for the cyclohexane, each carbon has 2 hydrogens, 1 hydrogen in the axial position and 1 hydrogen in equatorial position. 1 hydrogen in axial position and 1 hydrogen in equatorial position. Axial, equatorial, axial, equatorial. There are a few things you have to learn for cyclohexane, like a few facts, and then we put them all together. So 6 carbon, each carbon has 2 hydrogens. For every given carbon, one hydrogen goes up, one hydrogen goes down. For every given carbon, one hydrogen is in axial position, straight going up, parallel to the axial, and then one goes to equatorial. Equatorial kind of goes away from the carbon, and then axial is going to be straight up. So if I take this one as a carbon 1, I'm going to take one as a carbon 1, this one with the hydrogen that is no bond, so I'm going to mark this as a hydrogen 1. If for hydrogen 1, axial is down, for hydrogen 2, axial is up. For hydrogen 3, axial is down. Hydrogen 4, axial is up. The longer to record, this may be due to something. Okay. Okay. So any questions about the facts here? For axial and equatorial, each carbon has axial and equatorial, but the pattern is if the axial for one carbon is up, for the next carbon axial is down. This is the chair conformation. For the chair conformation, you have 3 hydrogens or 3 of these groups that they are kind of at the closer distance. So if this is carbon 1, that's carbon 3, this is carbon 5. We are going to spend basically today, the next, whatever is left, and then sometime tomorrow to look at the stability of the cyclohexane. What is the most stable configuration for the cyclohexane? But what makes the cyclohexane not stable based on the structure? So this is the chair conformation. We have 2 stable conformation for cyclohexane. One is chair conformation, and the other one is a boat conformation. See, when you make like a little boat here, and when you draw the boat, it's like this. So when you have the boat, is going to bring the 2 groups very close to one another. These 2 groups that are up here, the 1,4, is going to be very close to one another, and that makes the boat conformation not desired, very high energy. So chair conformation is more stable for cyclohexane compared to the boat conformation. Okay. Going to leave this here because you saw too much of the model. Going to go back to the slides and see what we left out. And I take with the structure for the cyclohexane because stability of the cyclohexane is completely different from other conformers. It's just based on if you have any branches attached to it. Why we spend so much time on cyclohexane? Because for cycloalkane, the only stable cycloalkane that we deal with is cyclopentane and cyclohexane. So we have to learn a lot more about cyclohexane compared to the to cyclobutane, because we just learned about cyclobutane, that is a 4-carbon cyclic system, is not stable, and under no normal condition that is going to form unless you really force it. Like cyclopropane, it exists in the lab, they can make it, but is not a stable compound. But when it comes to cyclohexane, you have to learn a lot more about cyclohexane, which I'm going to go back to the stability of the cyclohexane. For the conformers of, so we can go back to start from the cycloalkane. That's where we left on the slides. So what do we know about cycloalkane? The general formula is the CnH2n. Hybridization for each carbon, if we have a cycloalkane, still belongs to the AN family, alkane. Hybridization going to be sp3. Bond angle for cyclopropane is 60 degree. It's forced to be, that's the internal bond angle when you have a cyclic system. If you have a triangle, each one is 60 degree. And that makes cyclopropane very unstable. For cyclobutane, we have a 90 degree, and for 90 degree is unstable, is not as unstable as cyclopropane, but still is unstable. Cyclohexane, 5-member, hybridization is sp3. Hybridization sp3 and bond angle is 108. Cyclohexane, 6 carbon, 12 hydrogen, and hybridization for each carbon is also sp3. When you learn about hybridization, next step would be nomenclature. Just like alkane, we learn about hybridization, then we learn about the naming of this compound. How would you name a compound? This compound is called cyclobutane, but if there is a methyl group attached to it, it's going to be methyl cyclobutane. So it's going to be methyl cyclobutane. If you have 2 methyl group attached to the same carbon, it's going to be 1,1-dimethyl cyclobutane. That's for this compound. Now, if you have cyclohexane here, you take one of these carbon as carbon 1. You take one of the carbon as carbon 1, and then you have to number the rest of the carbons. Which one would take carbon 1? If it's alkyl branch, the one that is alkyl branch, it takes carbon 1. Now, which way should I go? Should I go to the left or should I go down here? I have to move in a direction that is going to take less distance to the next branch. So if I start carbon 1 here, this is going to be carbon 2, carbon 3, 4, 5, and 6. So we have to go down. So we have to go clockwise. Yes. So we have 2 methyl groups. One is going to be on carbon number 1, and then the other one is going to be on carbon number 3. So we give location of the branches first. If our branches are identical, we combine them, and we can use the di, tri, and tetra. If it's 2, for 3 would be a tri. Then we give the main carbon chain. So our main carbon chain here is our main carbon chain here is a cyclohexane, but we start with the branches first. So 1 and 3 here. So it's going to be 1, 3 dash dimethyl, because we have 2 methyl group, and the main carbon chain is not hexane, is a cyclohexane. If you have 2 branch, one is ethyl and one is methyl. Let's say I have a methyl group here. If I start numbering here, is going to be 1 and 2. If I start numbering in this position, it's going to be 1 and 2. Which one is more desired? Methyl taking 1 or ethyl taking 1? Because if methyl takes here carbon 1, then ethyl would take carbon 2. The rule, or IUPAC rule, says for cyclic system, if you have 2 branches, you are going to number from the side that it gives you lower number to a based on alphabetic order. So if we have ethyl group, preferably taking number 1 and methyl group taking 2 rather than the opposite. Okay, we don't want methyl to take 1 and ethyl to take 2. So methyl would be 2 here and ethyl is going to be 1. The name for this compound, which one should I write first? Also alphabetic order. So it's going to be 1-ethyl dash, because I have to bring the number again, -2-methyl, and then cyclopentane. So to name the branches, we have to name the branches first. We have to follow the alphabetic order, just like alkane first, and then the name of the major or main carbon chain. Because it's a cyclic system, we would use the word cyclo as a prefix to the to show the cyclic system, and then we say pent because it's 5 carbon, and then we say A and E because it's a saturated cycloalkane. Let's use an example. Let me see, I want to make sure I have the looking for empty page. Okay. So we have this compound and we try to name it. What would be the name for the compound? Which one should take one of the branches would take 1. Which one should take 1? The ethyl would take 1. Perfect, Annabelle. So we have 1 here, and is going counterclockwise or clockwise. We should go clockwise because the next one is going to be, the next branch is going to be on position 3. So we are looking for the lowest number. So with the lowest number assigned to branches, we should go clockwise. And we have 3, 4, 5, and 6. So we have a cyclohexane as the major or main carbon chain. We name the branches first in alphabetic order. 1-ethyl. Then we have 3-methyl. 3-methyl cyclohexane. That's when you have 2 branches. What happens if you have 1 branch only? If you have 1 branch only, you don't have to number it because is understood that is your carbon 1. So instead of saying 1-ethyl cyclohexane, you just say ethyl cyclohexane. So if you have 1 branch, no numbering needed, you just say ethyl or branch name and then cycloalkane. If you have 2 branches, you have to go with alphabetic order. You want to make sure lower number is assigned to the high priority in alphabetic order. So those are two scenarios. The next scenario would be you have more than two branches. What happens if you have more than two branches? Get the lowest branch number, perfect, or the lowest total of the numbers. When you add up the numbers, it has to add up to the lowest number. CH3 and CH3. Okay, the point of difference. Okay, which one should take one? Number one, in this case, if you get this one number one, there would be 2, 3, 4, 5, and 6. So we can go counterclockwise. It would be 1 plus 2 plus 3. And if you go opposite way, so if there is no difference in the numbering system, still you will go with the side that is the priority with the alphabetic order. If you have, say you have a methyl group here, then you have methyl group and a methyl group. Which way should you number it in this case? If ethyl takes 1, then it's going to be 2, 3, and 4. So you have 1 plus 3 plus 4. If methyl takes the 1, it's going to be 1, 2, 3, and 4. So you have two sets of numbers. It would be 1 plus 3 plus 4, or you have with the blue numbering is going to be 1 plus 2 plus 4. So 1 plus 2 plus 4, if you go 1 here for the methyl group, is going to give a lower number set. So 1 plus 2, this would be 7, and this would be 8. Which one is better numbering? It would be, we go with the lowest number assigned, so we have to go 1 for methyl group. Any direction that is going to give lower number set. So the red color is not going to be desired here, so we are not using these numbers here. We are using the blue color. So we go methyl 1, and the other methyl would be 2, and then we go clockwise instead of going counterclockwise. So the priority, it goes number in cyclic system, the number set, but if you have 2, it doesn't matter which way you go, the numbers is going to be the same. Since the numbers are the same, or the number set is the same, go with the alphabetic order. So what's the name for this compound? The name for this compound is going to be 1, 2. Why the pen is not behaving? Is going to be 1, 2 dash dimethyl for the 2-methyl group, and then your ethyl is going to be on the 4th position for ethyl, and then cyclohexane. But when you are writing, yes, lower number is more important than alphabetic order when it comes to giving the position to each of the branches. But when you are writing, you still write in alphabetic order. So you're going to name this as 4-ethyl, 1,2-dimethyl cyclohexane. So it's going to be 4 ethyl. So we name the branches first and then put them in alphabetic order. 1, 2, dimethyl, and cyclohexane. Okay. So the name for that structure, I'm going to have to draw it again because it's smeared like this. You have your ethyl group, methyl group, methyl group. So it's going to be numbered 1, 2, 3, and 4. So it's going to be 4-ethyl, 1,2-dimethyl, cyclohexane. Okay, that's for naming of cycloalkane. New term of cis and trans applies to cycloalkane also. If you have groups that are attached, if they are showing that one group is going down and one is going up, it's going to be named as trans. So just like the cis trans that we have for alkenes, here also for cycloalkane, if you have branches, that is show if you have 2 branches on cycloalkane and the 3D structure is given to you, you should name it as the branch, if it's cis or in the trans position. How do we know that these methyl group are on the same side? Because the triangles that are used here is showing as wedges, is not dash line. That means the first methyl group is going toward you, is up, and this methyl group is also up. So if both of them are on the same side, the position or the geometrical position for this is going to be cis. They are both on the same side. So it's a cis 1,2-dimethyl cyclohexane. And this is going to be trans because you have the dashes and wedges, with the dashes meaning that is going away from your view, and this is coming toward you. So one is up, one is down, or you could say one is higher than the level of your cyclohexane plane, and one is below. One is coming up, one is going down. Because they are in opposite side of the plane of cyclohexane, is going to be trans. So we have cis trans also. This is the geometrical isomers. You could have cis or you could have trans, because the rotation around carbon-carbon bond in a cyclohexane is not free, is not an open chain. Because it's not free, we can't say these 2 molecules are the same. This molecule A and B, they are 2 different molecules because you cannot rotate it freely. It's just like a cis and trans around carbon-carbon double bond. Shouldn't the dimethyl come first? When you are numbering, you give the numbers based on the number of the lowest number set. With the writing alphabetic order, it's followed first. It takes a priority when you are writing the name. So if you say 4-ethyl 1,2-dimethyl, is the still you can say, you can draw that structure based on the name. You could draw the right or proper structure. Let's say if I give you a name for 3-ethyl and 1,1-dimethyl cyclohexane. what would be the structure for this molecule? Substitute. The only good question, Ariana. The only prefix that is used in alphabetic order is iso. Iso counts, but the prefix does not count. I get your question now. The di does not count. The prefix is the name of the substituent that it counts. The only exception to that, I'm glad you asked the question, is going to be the iso. You have isopropyl, you don't count the P, you would count the I. But for di, tri, mono, you don't count those numbers, those prefixes, you would only count the substituent. That's a very good question. You're welcome. Okay, the structure for this molecule. So we practice how to draw the structure at the same time for cycloalkanes. First, we are going to start with the main branch. In this case, it's a cyclic system, so we draw a cyclic system. We can number it. So if we number this as carbon 1, 2, 3, we have the choice to go clockwise or counterclockwise. It's not going to make a difference when we are drawing the structure if the name is given. But then we have to follow strictly the positions that is given for each branch. It says 3-ethyl, so ethyl would go to this position. Ethyl group is going to use a 2 carbon, and then 1,1-dimethyl, so it's going to be 1,1-dimethyl. So you have your CH3 groups, 2 CH3 groups on carbon 1, and you have a CH2 CH3 group on carbon number 3 here. And that would be the structure. Any questions? The stability of the cyclohexane, it's very important, but first you need to know what cis and trans is, and then we learn about the equatorial and we are going to repeat the axial equatorial positions tomorrow and see if it's trans or cis, how they supposed to be for cyclohexane. It's kind of like if you were taking ACS exam, they emphasize on that a lot for any entrance exam that you were taking. The stability of cyclohexane is a big deal. And why is a big deal? Because they are trying to understand how much you can imagine 3D structures. This is basically the first structure that is going to challenge you. It's not hard. I promise it's not hard. It's just getting used to it. And if you cannot handle the structure, like understand this in MCAT, then they might think, well, it's very hard for you to imagine 3D. So you're not going to get the score that you need. So just try to build the skills to be able to imagine your 3D structures. We will work on it. If you have the models and if you build it at the same time I am, is going to be easier for you. So the molecular model that was suggested for you to purchase was for this chapter only. Actually, 2 chapters. Is one chapter 3 when you are dealing with cyclohexane, and then chapter 5 that you are dealing with the stereoisomers for enantiomers. If you don't have the model, it's going to be hard. And I'm sure I made many of you very frustrating with making models myself and showing you on the video. But if you had it yourself and you build it at the same time, it would be a lot more pleasant and it's easier for you to understand it. We will work on cyclohexane tomorrow. I'm going to answer the couple questions you have here, and I'm going to stop also